Hello, everyone. My name is Kentrell Ziegler, and today I'm going to walk through my Zybooks Chapter 12 project called Stable Storage. I'm going to explain it like a short IT training session, what stable storage is, why it matters, and how the system still reads and writes the correct data even when we have disk failures or a crash during a write. So let's start with what we're covering today. Here's the plan. I'll explain the concept first, then walk through how it's modeled in code, including bad block forwarding, stable read, stable write, crash simulations, and recovery. Then I'll show test results and connect it to real IT and cybersecurity operations. Let's begin with what the project is trying to accomplish. The objective is to simulate stable storage, which is a fault-tolerant storage method. The project wants us to handle two types of failures: bad disk sectors, represented as unreadable, and crashes during a write, where only part of the write operation completes. The goal is that after recovery, the system still remains consistent and correct values. Now, what exactly does stable storage mean? Stable storage is an OS reliability concept. Instead of trusting a single disk write, we keep two copies of each sector. If one copy is corrupted or unreadable, the system can recover using the other. This is important because OS components like file systems and logs depend on storage being reliable even under failure conditions. Next, I'll show how this project models storage using arrays. In this project, the two disks are represented as arrays A and B. Each array has N regular sectors plus M spare sectors. If a regular sector becomes bad, we don't just give up. We use spare sectors and mapping tables to redirect access. A bad sector is represented by the constant 0x octuple F, which means unreadable. Now that we understand the model, the next piece is handling bad blocks using sector forwarding. This is where the system becomes fault tolerant. If a sector is bad, instead of failing, we use sector forwarding. The function first tries to read the regular sector. If it's marked as bad, it checks the map to see whether that sector was remapped. If it was, the read is redirected to the spare sector at index n plus the spare number. Once forwarding exists, stable read becomes straightforward. Stable read means the system should return the correct value as long as at least one disk has a valid copy. We try A first. If A can't provide a valid value, either due to a bad block or missing mapping, we fall back to B. This is how redundancy protects us from single disk failures. Next is stable write, which is even more important because crashes can happen mid-write. Stable write updates both disk copies. The safe write order is A first, then B. If a sector is bad, the write is redirected to a spare sector. The main challenge is that a system crash can happen before both copies are updated. So the project also requires crash simulation and recovery. Now I'll explain the crash simulation, which would be the 5 possible ways a crash can interrupt the write. The crash function chooses a random sector R and simulates a crash while safely writing a new value. The project breaks this into 5 equally likely cases, from crashing before any write occurs to crashing after both are completed. The purpose is to test whether the recovery procedure can restore consistency regardless of when the crash happens. After a crash, recovery is responsible for making A and B consistent again. Here are the recovery rules. These recovery rules match the project instructions. If the crash happens before anything is written or after everything is written, no recovery is needed. If A was corrupted during the write, we restore A using the old valid value that's stored in B. If A has the new value, but B is old or corrupted, we copy the new value from A into B. The end goal is that both copies match and the system returns correct data after recovery. Next, I'll show the testing values or the testing results that prove stable reads and writes still work after crashes and media failures. All right, so here you can see the system start in a clean state. We initialize the regular sector, so AI equals BI equals I. And the stable read of all sectors outputs 0 through 9, which confirms both disk copies match. Next, I run the crash simulation. In this run, the crash reports a potentially corrupted sector, sector 5, and it occurred in case 2. Case 2 meaning that the crash happened while writing A5. So A5 could be corrupted while B5 still holds the old correct value. After that, I execute the recovery procedure. When we run stable read again, the output returns to the correct sequence 0 through 9. That tells us recovery successfully restored consistency and stable storage behavior after the crash. Now that crash recovery is working, the next test is handling an actual media failure when a disk sector becomes unreadable. This slide shows how the system handles bad sectors. First, I force a media failure by setting A sector 0 to the bad value. When I do a regular read of A sector 0, it returns 429.496.7295, which is 0x tuple f, meaning that the sector is unreadable. But when I perform a stable read of A sector 0, it still returns 0, which is the correct value. That works because stable read can full and fall back on the second disk copy, which is B sector 0, or use spare mapping if needed. Next, I simulate another failure at A sector 1, and then I perform a stable write setting A sector 1 to 1, 2, 3, 4, 5. The final stable read returns 1, 2, 3, 4, 5, which proves that stable write still succeeds even when the original sector on disk A is bad, because the write can be forwarded to a spare sector and kept consistent through both copies. With crash recovery and bad block handling both working, the stable storage system remains reliable under the main failure scenarios required by the project. In real environments, storage reliability affects everything, especially the operating system, file systems, logging, and incident recovery. If a crash corrupts logs or metadata, you can lose evidence or break systems. Stable storage concepts reduce that risk. From a cybersecurity viewpoint, preserving the integrity of logs in system state is critical for detection, response, and forensic investigation. Now, here are the key takeaways from this project. To summarize, stable storage works by using redundancy and recovery. 2 disk copies protect against single sector failures. Spare sectors allow remapping for bad blocks. Stable reads provide reliable access, and stable writes plus recovery handle crashes during updates. Overall, the system stays consistent and returns correct data even under failure conditions. These are the references used. The main source would be, of course, the Zybooks Chapter 12, Section 12.8 on stable storage. Thank you for watching.